Good morning everyone, this is Sandeep Kumar Sahu. Welcome back to our online class of iron making. This is the first part of our lecture 8. In this lecture we will discuss about various reactions that are taking place inside the blast furnace at different heights of a blast furnace. As per the height, the blast furnace can be divided into 3 zones. Okay, one is your upper zone or the preheating zone or the preparation zone. Okay, whereas the temperature is low. Okay, and then after the comes the middle part, that is the middle zone or the indirect reduction zone or the thermal reserve zone. Okay, or the isothermal zone. Okay, thermal reserve zone we have studied about that, where the temperature remains the constant with the height of the blast furnace. And then the lower zone, that means above the tour, just above the tour, that is the lower zone or the processing zone or the melting zone, where the direct reduction taking place. That's why it is also called as direct reduction zone. So let's this is the figure we have seen in our previous class. This is the top part is called your upper zone. Okay, where the temperature is low enough and the temperature is increasing. This is the solid temperature. Okay, this is the solid temperature. The red line one is the solid temperature, and then the dotted line, this one is your gas. Dotted line is your gas. Okay, so we have seen that the dotted line is always right to the that of the solid line. That means the gas temperature is higher than that of the solid temperatures. But after the preheating zone, okay, the upper zone or the preheating zone, after the upper zone, the middle zone has a we can see that in the middle zone the temperature is constant. Temperature is constant with respect to the height of the blast furnace. So this is also called as thermal reserve zone. That means with respect to height of the blast furnace, the temperature is not changing. The thermal reserve zone. Within this thermal reserve zone, okay, there is a chemical reserve zone or the chemical inactive zone, where the iron oxide, that means the FeO, and the carbon monoxide gas are in equilibrium. Okay, so this is also included in the thermal reserve zone. Okay, so or the middle zone. Then after the lower zone is just above the tour. What is the tour? Here it is the tour 0 means this is y-axis is the distance from the tour level. So 0 means it is the tour, and the 20 meters means it is the stock lines. This is the stock line. Okay, this is the tour. Okay, so just above the tour to about 4 to 5 meters height, this is called your lower zone, where the melting and the direct reduction taking place. Melting and the direct reduction. Direct reduction means reduction where the carbon is involved. Generally, we are talking about the indirect reduction, that is reduction by carbon monoxide. That is the indirect reduction, but here the carbon is involved in the reactions. So this is called your direct reduction zone. Okay, above that, both the two zones are also called as indirect reduction zone. Okay, this is called the indirect reduction zone up to this, and this is your direct reduction zone. Okay, we have studied about this, all this about. Okay, so first of all, let's talk about the reaction in the top part, that is the upper zone of the blast furnace. So there is always difference between the solid temperatures and the solid and the gas temperature. Gas is always higher than that of the solid temperature. So the solid temperature is ambient to 800 degrees centigrade. Okay, ambient means when we are charging the raw material, it is at the room temperature at the top. Okay, and the ascending gases, okay, ascending gases at the bottom of the upper zone, it may be about 1000 degree, 800 to 1000 degrees centigrade. And when it comes to the top part of the blast furnace, during the exit gas temperature, it is about 250 degrees centigrade, or maybe as low as 100 degrees centigrade also. Okay, So the different reactions taking place inside the upper zone, and the most important one is your reduction of your iron oxides. Iron oxides reduction. We generally have iron oxide, that is the hematite as the raw material, and the sinter and the pellets made up of this hematite ores. Okay, so this hematite is reduced to magnetite, and magnetite is to austenite, and finally this is reduced to iron inside a blast furnace. Okay, all these reactions, can take place in this upper zone, but preferably the hematite to magnetite reduction is instantaneous. Instantaneous. Why it is instantaneous? We have studied that when we are talking about the dissociation pressure oxygen associated with this hematite. Okay, so when we are talking about the Ellingham diagram with respect to partial pressure of oxygen, that means the Fe2O3 is at the top of the figure, means the plot, showing that it has high oxidation potential and highly unstable. So little amount of carbon monoxide can reduce to its lower oxide, that is your Fe3O4, that is the magnetite. Okay, so it is instantaneous. This reaction is instantaneous and completed within this region. And magnetite to austenite is also taking place inside this region. Okay, and FeO to Fe, this reaction is not completed within this region. All these reactions are indirect in nature. That means carbon monoxide is involved. All these reactions. Okay. So these are called the all indirect reductions. Okay. Generally, magnetite is reduced to austenite mainly in the temperature zone of 700 to 900 degrees centigrade. Okay, 700 900 degrees centigrade. So it may be taking place at the bottom of the upper zone, but FeO is not completed in this upper zone of a blast furnace. And these actual reduction depends upon the size and nature of the ore and the intensity of the gas flow in the radial cross section of the blast furnace. So the size of the particles, that means the iron ores or the iron oxides, also determines its reducibility, because if the size is low, then the surface area will be more, so the reducibility will be increasing. Okay, and the nature, we have studied about the different aspects of iron ores, that means the how to choose good iron ores, or the how rich it is, and what are the gangue materials. We have evaluated how to evaluate the iron ore. So in that region also, the type of gangue material associated with this ore plays an important role for its reducibility also. Okay, so we have to choose the iron ores with less amount of gangue and preferable impurities inside the raw materials. Okay, next comes the devolatilization. Okay, the water left in the coke, ore, limestone and other charred material are very helpful for lowering the top gas temperature. Generally, our target is to decrease the top gas temperature and utilize maximum temperature sensible heat of the gases inside the blast furnace. So we have to generally this water, left out water, is very helpful for this decreasing the lowering the temperature at the exit. Also, water is deliberately added to decrease the dust loss in the top gas for the ore fines. We generally know that there is no chance of adding iron ore fines as a raw material inside the blast furnace, because it is operated at high temperature, and due to this high velocity of gas, there will be dust nuisance, and that will increase the load on the gas cleaning system of a blast furnace. So we generally do not prefer the fine ores or ore fines inside a blast furnace. Okay. In that case, if there is some amount of fines, then this left out water can be used or helpful for decreasing this dust nuisance. Okay, the devolatilization of water, that means chemically uncombined water, that means in the form of moisture in ore, coke and limestone. Okay, this requires about 580 kilocalorie per kg of water. Okay. And also we know that a good quality of coke also have about 1.5 to 2% of volatiles. So this has to be eliminated, or these are eliminated during the top part of the blast furnace. Okay, okay, okay. Somewhere it may be treated as drying. Somewhere it is also called as drying. Okay, but apart from this, physical water, that means physical presence of water as moisture in the burden, it may be present at the combined water, chemical combined water, or hydrates. Okay, so this decomposition of these hydrates of iron oxide can start at 300 degrees centigrade, whereas your moisture repellation can be taken as 100 degrees centigrade. Okay, it is at a higher temperature zone. Okay, so energy needed is about 965 kilocalorie per kg of water. So that means it is somewhat higher. That means how much hour? The additional 385 kilocalorie per kg is used for what? It is used for breaking the bond of hydrogen. Then after it is evaporated, means it is gasified. But before that, it has to the bonds are broken, which needs about 385 additional energy to break these bonds. So decomposition hydrates. So requires higher energy, and it takes place at somehow lower part in the upper stack. Okay. The hydrated water may react with carbon monoxide to produce carbon dioxide and hydrogen. This is called your water gas shift reaction. Okay, water gas shift reaction. CO2 plus H2O gives rise to CO2 plus H2. Sorry, CO plus H2O gives rise to CO2 plus H2. Okay, it is thermodynamically possible to produce thermodynamically possible for this reaction to be feasible inside the upper part of the blast furnace, means the upper zone. Okay, but it is kinetically more favorable in the middle zone because it takes place about 800 to 1000 degrees centigrade. Okay, if we look at the thermodynamic data, then the equilibrium constant of the reaction is 2.46 at 900 Kelvin and 0.8 at 1200 Kelvin. So it is thermodynamically possible in the upper part, but kinetically it is more favorable at the middle zone of a blast furnace. And for this class, the final reaction is our carbon deposition reaction. We know that carbon dioxide plus carbon gives rise to 2 carbon monoxide. This is called your Borward equilibrium reaction. Borward equilibrium reaction, the forward direction reaction is called your solution loss reaction. That means carbon dioxide plus carbon gives rise to carbon monoxide. This is solution loss reaction. And the backward direction reaction, that means 2 carbon monoxide gives rise to carbon dioxide and carbon. Okay, this is called your carbon deposition reaction. Okay, carbon deposition reaction. So this can be carried out at some active surface or the active sites. Okay, what are the active sites? It may be the surface of the ore, okay, or any surface, or in the pores of the sinter or the pellet, or inside the refractory brickwork. Okay, these are the active sites for reaction or the carbon deposition reactions. Okay, this reaction has a prevailing effect on your blast furnace parameters. For example, it economizes the fuel consumption. How it can economize the fuel consumption? As we know that the carbon is produced in this reaction, and it is used again for your formation of reducing gases. So when we are talking about the solution loss reaction, that means the carbon is lost or come into the solution due to this solution loss reaction. That means the reverse of this carbon deposition reaction. So in carbon deposition reaction, it economizes the fuel consumption by preserving the carbon. Okay. And rapid heating of the charged material. Rapid heating of the charged material, that means as this reaction is exothermic in nature, as we have seen that this reaction produces about 41210 calorie. So it is exothermic reaction. At the point of contact, that means the point of reaction, the temperature of the raw material increases rapidly. Okay. And the most important effect is the permeability of the burden. It alters the permeability of the burden. This is your most important parameter for this carbon deposition reaction. It alters. It doesn't favor or unfavor. It alters. That means in both way it has effect. For example, when the carbon deposition reaction takes place inside the pores of a blast furnace, sorry, inside the pores of the iron ores or the sinter pellet, okay, then at that pore carbon monoxide will be formed, and that carbon monoxide when formed, the volume will be increased, so the particle will break and form fines. Okay, so that fines will be a problem for your bed permeability. That means it will clog the pores or the voids of the bed of the blast furnace raw materials, so that the passage of the gases are blocked. So it will hamper the bed permeability by this carbon deposition reaction. Okay, and also the fine particles of carbon also clogs the pores of raw materials, so that the diffusion of the gases inside the raw material will also be hindered. So in one way, it is decreasing the bed permeability. This carbon deposition reaction, in one way, is decreasing the bed permeability, but in other way, that means when the carbon soot is formed around the raw materials, that means the sinter or the pellet or the iron ore, okay, then what happens when temperature increases at the point of contacts, then agglomeration generally occurs. But as we know that carbon has high melting point and it also acts as a lubricant, so the smooth descent of the burden occurs without agglomeration. So in that way, it can help in the maintaining the bed permeability. So it has both way effect. That's why it has written that it alters bed permeability of the burden inside a blast furnace. Okay. As the particles of the carbon are very tiny, so during the course of reaction or the process of the iron making inside a blast furnace, we are using high velocity gases. That means the from the 2 years high velocity air or the blast is input into the furnace, so that it can overcome the pressure drop. So these tiny particles cannot withstand that much of pressure, or it will fly away into the outgoing gases. Okay, so it will decrease its efficiency of carbon deposition. Okay, it is driven out by the high velocity ascending gases into the gas cleaning units. Okay, and we know that uh, 2 carbon monoxide, because this reaction in this reaction 2 carbon monoxides produces 1 carbon dioxide. I am talking about the gases only. Okay, all the gases. 2 carbon monoxide forming 1 carbon dioxide. That means the volume of the gases is decreasing. That means the volume if decreases, then it can sustain high pressure. Okay, that means in other way we can say that height of pressure helps in this carbon deposition reaction, because higher the pressure, this reaction will be more preferable. because if pressure is high, then this reaction goes in the forward direction. Okay, and also the carbon produced by this carbon deposition reaction may be deposited, okay, may be deposited into the walls, okay, into the walls of the shaft, and can cause its disintegration, dislocation, as well as formation of bridges and accretions also, because combustion of carbon will lead to high temperature, and that will cause formation of bridges. That means it will raw material will be sticking to the walls. Okay, that means formation of early slag, and that will be solidified. That will be creating bridges and accretions also. Accretions means ring type, continuous ring type. Formation of raw material sticking to the wall of the blast furnace in the stack region. Okay, so these are the advantages as well as disadvantages, or in total the effect of carbon deposition on the blast furnace reactions. Okay, blast furnace process. Okay, so last one is your decomposition of carbonates. Okay, decomposition of carbonates means generally we are using the dolomite inside a blast furnace for as a flux. So it contains MgCO3 and CaCO3. Okay, MgCO3 and CaCO3, and when this is exposed to higher temperatures, that means about 450 degrees centigrade. Okay, MgCO3 will be decomposed, but your CaCO3 requires higher temperature, that may be 900 degrees centigrade and above for decomposition. So except the calcium, other carbonates will be decomposed within this region. That means the MgCO3, that is the inside the that is the MgCO3 which is in the dolomite, that will be decomposed, but the calcium carbonate will not be decomposed within this region. Okay, these are all about the reactions inside a blast furnace taking place in the upper part of the blast furnace, that means in the upper part of the stack. Okay, so thank you all. If anyone has any doubt, they can ask.